So this synthesis chapter is largely review, and it's sort of putting together a lot of the reactions and the concepts that we've learned this semester. And so I don't have a whole lot of new videos, but I did want to highlight reactions that are capable of changing the carbon skeleton. So for some synthetic transformations, it may be necessary to alter the carbon skeleton. Right? What I mean by that is adding or removing carbon atoms. And so we need to remember what reactions are capable of doing this, because most of the reactions that we've learned so far only change the functional group or change its location. And so the reactions that we've learned that can increase the number of carbon atoms are terminal alkylation of alkynes. And then we covered this briefly, and so I spend more time on this video, but in the organometallic chapter, which we covered when we did chapter 7, we learned about Gilman's reagent, and so I wanted to talk more about that because it's capable of increasing the size of our carbon chain. And then the reactions that we've learned so far that can decrease the number of carbons are ozonolysis of either alkenes or alkynes. And then in Orgo 2, we'll learn a lot of new reactions that can be used to alter the carbon skeleton. But these are the ones that we've learned to this point. So first is terminal alkylation. And so we learned this reaction in the chapter about alkyne reactions. And so if you remember for this reaction, if we take a terminal alkyne and we react it with a strong base, that strong base is capable of deprotonating our alkyne to produce this alkanide ion. And then this alkanide ion is a good nucleophile, so if we introduce it to an alkyl halide, right, we can get an SN2 reaction to make a new carbon-carbon bond. And so the way this would look for a synthesis problem, right, if I was trying to achieve this transformation, right, if I first used our strong base, NaNH2 is I think one of the more common ones that we use, and then if I react this with ethyl iodide, right, I can attach an ethyl group onto my original alkyne. And then we can make this alkyl halide, in principle, whatever we want. Now, that being said, this is an SN2 process, so if you remember on our discussion of SN2 reactions, right, those work best for primary alkyl halides, they're slower for secondary alkyl halides, and they're not going to work at all for tertiary alkyl halides. So when we talked about organometallic compounds, we talked about lithium dialkyl cuprates, or Gilman reagents, and these compounds are also capable of creating carbon-carbon bonds, and we can do coupling reactions with alkyl halides to produce new carbon-carbon bonds. And so let's talk about these a little bit more. So these Gilman reagents work best when I react them with methyl primary, vinyl, or aryl halides. And so these are all good alkyl halides to react our Gilman's reagent with. It turns out tertiary halides and most secondary alkyl halides give elimination products. So we're really looking for methyl primary, vinyl, or aryl halides. A big advantage of the Gilman reagent over some other organometallic compounds is that they're fairly selective. And so we can use these even when other functional groups are present that other organometallic compounds might react with. So sort of thinking backwards, if I have two alkyl halides that I want to connect together, right, I can turn one of them into a Gilman's reagent, react that with the second alkyl halide, and I'll get my coupling product. And so the way this synthesis would look, so first we need to make the Gilman's reagent, and so I can do that with 2 equivalents of lithium, and then hit it with copper 1 iodide, and that will produce the Gilman's reagent with the first R group. Then if I take the second alkyl halide, I can react it with the Gilman's reagent that I made and produce the coupling product. So this is a very useful reaction for increasing the carbon skeleton. Okay, then the last slide here. The one reaction that we've learned so far that can be used to decrease the carbon chain is oxidative cleavage, or ozonolysis. So if I take an alkene and hit it with ozone and then DMS, I can then break this carbon-carbon double bond, and I produce two compounds with carbonyl groups. I can do a similar reaction with an alkyne. In that case, I'd use ozone and water, and then that breaks it up into two carboxylic acids. And so in the second semester, we'll learn a lot of new reactions that can be used to alter the carbon skeleton.